Friends, welcome to PSCAD tutorial. In this tutorial, we will learn the distance relay in PSCAD. Uh, so in this video, it is difficult to learn the basic of transmission line protection and PSCAD model in a single video. So I will make the first video, that is part 1, the basic of transmission line protection. In the next video we will learn the PSCAD modeling. Okay, so first, part 1, basic of transmission line protection. Okay, now this is the part 1. So we need to learn the transmission line protection. For that we have to build a transmission line. This is a generator, this is a bus bar. So this is a line, and this is line impedance. This is again a bus, this is again a transmission line, this is bus, and this is the receiving end generator. So do it, say VS, and this is say VR, and this is bus number 1, this is bus number 2, and this is bus number 3, right? Say in the bus number 2 there is a load, there is a load connected. Okay, now here a breaker 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 is here, and our relay, that is the relay is placed here, which gives the trip signal to this breaker. So if we create fault here, it must sense the current and voltages here, and give the trip signal to the breaker, and it will trip this line. Okay, so this is a fault. So in transmission line protection we use distance relay, because we can use the differential relay also, but in transmission line the length is very large, so the pilot wire of the differential relay, it will cost more. So it is uh, uh, easy to use the distance relay. So distance relay operation is nothing but the impedance operation, that is Z equals to V by I. Okay, and simply when a fault occurs, current flowing through the circuit is increased, so this current will increase, and automatically our Z will decrease. So if we set Z, say set value of Z is greater than our transmission line impedance seen by this relay, then it will give the trip signal. Okay, this is the basic of distance relay only. Now transmission line protection. So transmission line protection, this is okay. Now if a relay is placed here, relay is placed here, in case of distance relay, the more relay is used for long distance transmission line, and there are some impedance relay, admittance relay also, but more relay is used for long distance transmission line. So here if we install a more relay, then it will protect up to 80% of the transmission line, instantaneous protection. So this is 80%. Okay, so if we write, this is line 1 and this is line 2, our zone 1 protection, we can say, if this is ZA and this is ZB, so this will be 80% of ZA, right? Which is given, if we draw a time axis, and this is length, this is time. So Z1 will give 80% instantaneously with no delay, no time delay there. It is observed there is no time delay, right? Now uh, it will give also protection of the rest of this transmission line 20%, which Z2 equals to 20%, means this is 100% actually Z of ZA plus 20% of the next line. 20% of the next line means ZB. Okay, so but there is some time delay. There is some time delay. So if this is 20% of line 2, the up to this it will give also the protection, but there is some delta T1. This is a time delay. Okay, now there is a backup protection facility is also in the more relay, that is our zone 3 protection. It will give the 100% 100% protection of the line uh, A, line 1, and plus 40% of the next line ZB, the 40% of the next line. So it will give the protection extra 20% of the zone 2, and there are some more time delay is needed. So this is, if this is our 40% of the line 2, up to this we need some extra time delay. So this is T1 and this is our delta T2. Okay, so this is transmission line protection, basic of transmission line protection. Now if we draw the impedance plot, impedance plot uh, this is our resistance and this is uh, reactance, right? Now this is our if we draw three circle here, actually this is circle, this is not accurately I can draw the circle, but this is circle, exactly circle. So this is our zone 1 and this is our zone 2 and this is our zone 3, right? So if we draw the a line, and this is our 80% of the transmission line, this is our 100 plus 20 means 120% of the transmission line, and this is 140% of the transmission line. Now, our apparent impedance seen by the relay, if we go back to the figure, in this case, if there is a fault occur here, say 70% of the transmission line, and there is a fault. So it will be inside the zone 1, as zone 1 is 80% of the transmission line, right? So if we see the apart impedance curve, it will goes like this and go inside the zone 1. Okay, if there is no fault occurs, the apart impedance go beyond this 3 circle, but in case of fault, the apparent impedance will move inside the zone 1 in case of 70%. Up to 80% any fault, it will go inside the zone 1. Say there is a fault occur in the bus 2, or say 110%, 120%. This will come this way, and the apparent impedance will move inside the zone 2. Then apparent impedance this on zone 2. Okay, if say 140%, up to 140% there is a fault, say 140%, actually if we assume the z actually line 1 and line 2 have same length, this will be 140%. Otherwise, this is 100% and 40% of this line, so this may not be 140% exactly for all the cases, only in case of line 1 equals to line 2, length of the line 1 equals to length of the line 2. So if in case 140 percent, there is a fault, it will come in Z3. So this is instantaneous protection. This is uh, a protection with some time delay. This will also have some time delay, and this is called, actually zone 3 protection is called actually backup protection. Means there is also a relay installed in this line, for this line also. So if we if there is a fault after this relay, means if this is relay 1 and this is relay 2, then relay 2 obviously it will operate, and 140% of the transmission, there if there is a fault, then relay 2 will obviously operate. But in case of relay 2 failure, there is a backup protection given by relay 1. Okay, so the zone 3 protection is actually called backup protection of the transmission line. So this is the basic things of uh, transmission line protection. But we have 10 types of faults. Means actually type is our line to ground fault, double line to ground fault, line to line fault, and three phase fault. Okay, so line to line fault, there is if we say um, phase A, phase B, phase C, there will be A G, B G, and C G fault, and this in this case A B G, B C G, C A G fault. In this case A B, B C, C A fault, and in this case A B C fault. Okay, so now 3 plus 3 plus 3 plus 1, that is equals to 10 types of fault we can observe. In the all this fault, the fault actually Z apparent impedance, the formula is not exactly for all kinds of faults. There are different. In the next section, we will discuss uh, the calculation of apparent impedance seen by the relay for different types of faults. Okay. So in this section we'll learn the apparent impedance, seen by the resistance relay. Okay, apparent impedance seen by the resistance relay for various kinds of fault. So we need to build a diagram. Say this is our generator, star connected generator. This is say our voltage EA, this is EB, and this is EC. Okay. Now suppose this is bus. Okay, and here circuit breaker is placed. This is our circuit breaker CB, and here also the relay is also placed here in this location, relay. Now current flowing through this conductor is IA, and this is IB, and this is IC, right? Now this is impedance, say this is impedance Z of the transmission line. So in case of say LG fault, line to ground fault, single line to ground fault. Okay, so suppose there is a fault occur in the line A. Okay, so this is in the line A, that means this is a AG fault, right? So if we draw the sequence component diagram, this will be like this. This is our generator positive sequence component, positive sequence, negative sequence, and zero sequence. This is our let me draw the diagram first, then I will explain. Say this is our source impedance 1, source impedance, this is negative sequence component, and this is zero sequence component, and this is our line impedance Z1, Z2, and Z0. For transmission line, Z1 equals to Z2. Okay, so now current flowing through this is IA1, this is IA2, and this is IA0, and this is VA1, VA2, VA0. So this is the sequence component equivalent circuit. So in case of AG fault, we need to connect this. So the positive sequence generated EMF is connected to the positive sequence component. Then it will connect like that. Now this is like that, and this is the connection. Okay, so this is the connection for line to ground fault. Okay, Now this bus voltage, in this bus location there is a relay, so our voltage seen by the relay is this bus voltage, and current seen by the relay is this currents. Okay, now say our VA, for AG for the VA we have to calculate VA will be nothing but the uh, addition of the sequence component of all these things. Okay, so VA1 will be our IA1 Z1 plus IA2 Z2 plus IA0 Z0. As we said that for transmission line Z1 equals to Z2, we can write as IA1 Z1 plus IA2 Z1, and we add a component IA0 Z1 plus IA0 Z0, and we need to subtract this. So IA0 Z1. So this will be, if we take common Z1, this will be IA1 plus IA2 plus IA0 is nothing but IA, plus if we take common IA0, this will be our Z0 minus Z1 into IA0. Okay, now uh, if we take Z1 common, then this will be IA Z0 minus Z1 by Z1 IA0 and into Z1. So our apparent impedance Z seen for line to ground fault exactly our positive sequence impedance, that will be our VA divided by IA plus Z0 minus Z1 by Z1 into IA0. Okay, and this can be also written as VA by IA plus Z0 minus sorry. So this is our K0 IA0, where K0 is equals to Z0 minus Z1 by Z1. Okay. Uh, in this case, this is actually AG fault. In case of BG fault, this will be VB by IB plus K0 I0, and in case of CG fault, actually Z equals to VC by IC plus K0 I0. Okay. So this is in case of line to ground fault. Okay. Uh, for line to line fault, and also double line to ground fault, the equations are the same. Here, if we draw the sequence component equivalent sequence component diagram, the zero sequence will remain open circuited, and positive sequence and current sequence are in parallel. So face to face fault, always remind that in case of face to face or face to face in double line to ground fault, um, is represented by the parallel combination of positive and negative sequence components. So this is our positive sequence uh, generated EMF, and this is ZS1, this is Z1, ZS2, Z2, and in this case this is like connected like this, and it is connected like this. So this is the connection. So in this is IA1 and this is IA2. This is VA1, this is VA2. Okay, so if we take a KVL here, from here to here, this will be our VA1 minus IA1 Z1 minus IA2 Z2 minus VA2 equals to 0. So VA1, if we take the voltage in one side, and in case of transmission line, we have already said that Z1 equals to Z2. So if we take common Z1, then this will be IA1 minus IA2 Z1. So our Z seen will be our Z1 equals to VA1 minus VA2 divided by IA1 minus IA2. This formula is for all types of line to line fault and double line to ground fault. In case of say BC fault, so we need a term in terms of B and C. So uh, now say VA, we know that VA VB VC is equals to square A. This relationship we all know. We all know this relationship where A is just magnitude 1 and angle is 120 degree. So this will be 2 pi by 3. This is known to all. So VB will be VA0 plus A square VA1 plus A VA2, and VC in case of BC, say BC fault. So we need to calculate VB and VC and IB and IC. So this will be our VA0 plus A VA1 plus A square VA2. In case of IB also, IA0 plus A square IA1 plus A IA2, and IC equals to IA0 plus A IA1 plus A square IA2. So in this case, if we just subtract VB from VC, this will be A square minus A VA1 plus A minus A square VA2. Okay, so if we take common A square minus A, this will be our VA1 minus VA2, and at the same time if we do VIB minus IC, this will also A square minus A IA1 minus IA2. So if we write VB minus VC divided by IB minus IC, this will be our VA1 minus VA2 divided by IA1 minus IA2. So that is equals to ZC now. So we can express our ZC in terms of the phasor component of that particular fault. This is for BC fault, and in case of AB fault, this will be VA minus VB by IA minus IB, and in case of AC fault, this will be VA minus VC divided by IA minus IC. Okay, so this is for line to line fault and line to ground fault. And always remember, we all know three phase fault, our Z scene is always our positive sequence voltage divided by positive sequence current. So it is no need to build this thing. So if we now we need to draw the control circuit diagram. So if we get back to this and copy these things and go paste it here. Oh, I need to copy this thing. Okay, whether it can be pasted or not. Yes. Okay. Now to erase this thing. This is our diagram, right? Now I need to erase these things also, and also erase these things. So this voltage our VAB, this is VBC and VCA. We can get it from here. Okay. Now if we measure the current, the CT is connected like this. So first I draw the connection, then I will explain this. So this is our IA, this is our IB, and this is our IC. So this will be IC minus IA, this will be IB minus IC, and this will be IA minus IB, right? And if we take, if we want to uh, get the zero sequence current, this is our residual current actually. which is IA plus IB plus IC, and that is equals to 3I0. Okay, we can calculate the I0 from here also. So this is the diagram, and now we need to build the control circuit diagram which will give the trip signal to the circuit breaker. So this will this currents and voltages are sensed by this relay. So actually relay oops relay control diagram is shown in this figure here. This is our set value of Z. We need to just compare. This is nothing but the comparator. So this is VAB. VAB means VA minus VB, and we give the signal IA minus IB. This is VBC, and we give the signal IB minus IC, and this is CA, and this is IC minus IA. Right? We give this signal to the comparator whether the impedance in by the relay is less than our Z set value or not. And in case of line to line, this is for line to line or double line to ground fault. This is our LG fault, and this is VA divided by IA plus K naught I naught. This is for BG fault, IB plus K naught I naught, and this is VC, and this is IC plus K naught I naught. So this is for LG fault, this is for double line to ground fault or line to line fault. And there is no need to write the for three phase fault, because you can write, but it is not necessary, because if this fault is detected and this fault is detected, this will automatically our ABC fault. So we need to draw OR gate. Sorry, need to draw a big OR gate here. If any of this give the signal 1, this can or 1 or 0, 1 or 0, 1 or 0. Okay, oops. So this is 1 or 0. This is 1 or 0, and this is also 1 and or 0. If any of this gives the positive 1, means there is a fault in that particular phase, or if, between the phase, this OR gate will energize and it will give the trip signal to the circuit breaker. Okay, so this is the control circuit of the distance relay. So after this uh, we can by this concept we can build a PSCAD model. So this is the basic of transmission line protection for part 1 video. Then next video, this is part 2, PSCAD modeling we will done will be we'll look for PSCAD modeling in the second part. So this is end of this video. Thank you.